What's up, everyone? It's Paul Footwear here. Welcome to another episode on the Acing the Coding Interview Data Structure series. So, welcome to the part B of this series. So, in the part B, we'll be looking at the non-linear data structure. So, stay tuned and try as much as possible to watch the previous episode so that you can get a hang on this current episode. Welcome to another episode on the Acing the Coding Interview series. So, in this episode, we are going to be looking at one special kind of tree and the most common kind of tree, and that's the binary tree. So stay tuned and pay rapt attention. So if you're new to this series, I advise you to go and watch the first episode so that you can understand what we are doing in this series and understand data structures better. So the binary tree is a kind of tree where every non-leaf node has the maximum of two child nodes. So that's simply the definition of a binary tree. As the name suggests, binary, that means two. So it has the maximum of two child nodes. That's every non-leaf node. A non-leaf node is a node with children nodes. So we'll be looking at more terminologies associated with binary trees and trees at large. In the last episode, we talked about most of these terminologies, but we are still going to revisit some and also uncover new ones. So here are some common terminologies associated with binary trees. So we have the root node. So the root node is the firstmost node in a tree. So this is where all other nodes originate from, like a root in a tree, where the tree grows from and collects, sucks, gets its nutrients from. What helps the tree get nutrients from the ground? That's how the root node is in binary trees. It's what gives birth to the other nodes. It's like the ancestor of all nodes in a tree. So next we have the parent nodes. So these are nodes, the nodes that give birth to other nodes that have children. And we have the children node. The parent nodes can also be called non-leaf nodes if you're looking at it in a collective way. But you can call a node a node that give birth to another node. So that node is a parent node. And if you want to address it, let's call it independently, you can call it a non-leaf node. So next we have children nodes. These are nodes with parents. Next we have sibling nodes. So a sibling node is more like in real life families when we nodes that share the same parents. So a sibling node is a node that share the same. Are nodes that share the same parent node. So we have leaf nodes. So these are nodes without children, and they are always at the bottom of the tree. So they are the last nodes in the tree. Next, we have what they call balance. So a tree is said to be balanced when all the leaf nodes are on the same level. So we are going to talk about the level terminology, the term called level in tree. So the next terminology we have is the traverse. So whenever you hear traverse, it means moving through a tree, carrying out an operation by moving through a tree. The next thing we have is an edge. So an edge is a connection between nodes. So just like parents to children, that's line that connects with the parents and the child. That is called an edge. So you may not be able to like visualize it as I'm saying it orally, but I'm going to draw up a picture and use that picture to explain most of these terminologies I mentioned here. So the next we have is a path. A path is a sequence of connected edges. So we'll be looking at it in the visual depiction. Next we have is what's the next term we have here is the level. The level term. So as the name suggests, it is just a position on a particular path. Just like levels in real life, stage after stage. So the topmost level is the root node. The root node has the topmost level, followed by the next node, followed by the next node, followed by the next node. So you wouldn't really understand what level actually means till you see a visual depiction explaining these terminologies. Next we have is the height. The next term we have is the height. So the height is just the maximal part or the maximal length that you can get in the binary tree. So many people confuse it with size. Size is the number of nodes in a tree, but the height is the longest part you can get from the tree. the maximal part you can get from the tree. So with a visual depiction, you'll be able to get what we'll be able to explain each of these terminologies in a way that you can understand it better. So here is a picture of a binary tree. So I'll be using it to explain the terminologies that I aforementioned. So we talked about children nodes. So 1 and 2 are like our child nodes of 0, which 0 is the root node of this particular tree. As you can see, is the ancestor of every node in this tree. So talking about levels, the topmost level is the root node, which is 0, and the topmost level is given the key of 0. So you can, just like in arrays where the first node has the index of 0, that's how levels are like. Levels are just like positions on the path of a tree. So like I said, edges are just connections between nodes in a tree, like how 0 and 1 is connected. Then paths are sequence of connected edges. So 3 is connected to 1 and 1 is connected to 0. So you can say there's a path from 0 to 3. So we talked about height. So height is the maximal part you can get from a tree. The longest part in a tree is the height of the tree. So the longest part in the tree is the part from 7 to 0, and which is, you got 1, 2, 3. No, 1, 2, 3. Yeah, which is 3. So the height of the tree, of this particular tree, is 3. So that's it for those terminologies that were pretty confusing when I was explaining it orally. So with this visual depiction, I believe that you'll be able to understand it better. So paths run from every path ends at a leaf node. That means a node without a child. Like you can see, in the case of 6, the length of the path is 2. So that's why it couldn't be the height of the tree, because there's a path longer than it. So every path just ends at a leaf node in a binary tree. So next off, we'll be looking at some constraints, some rules governing the implementation of binary trees. So you can call them features governing binary trees. So here are the features of a binary tree, and these features, they also govern how the binary trees will be implemented, because in this video we are going to look at the implementation of binary trees. So the first feature we have there is that each non-leaf node has 2 children maximum. So every node that has children in a binary tree can't have more than 2 children. The second feature is that it has only one root node, so it can't have more than one root node, unlike the B plus tree that can have more than one root node, like 4 nodes can even be this root. So the next feature and the last feature, there are other features, but they are not really that important in regards to the implementation. So the bigger child node is kept at the right edge, while the smaller child node is kept at the left edge of the tree. So you can see edges as kind of like branches in a real world, like in a tree in the real world. So like I said in the last clip, the last session on, that was in the visual depiction about how the nodes which are bigger are kept at the right edge, and then the ones that are smaller kept at the left edge. So that's one of the features, one of the major features that governs the implementation of binary trees and how they behave. So like almost every data structure we've treated in this series, we always start the implementation with the node class of the data structure. So that's what we are going to do with the trees. And remember, these are all pseudocodes, meaning they're just an imaginary code trying to represent the concept of the implementation. So we start with defining, like implementing a node class. There's this node class is what governs every node object, every node that's going to be in the tree data structure, the binary tree data structure. So let's run through the pseudocode. So you can implement this pseudocode in any language of your choice, so be it Python, JavaScript, C++, any language of your choice, as long as you just understand the concept. So first we declare the class node, then this is the initialization method. So whenever the node object is initialized, this is what loads up the value attribute, which carries the value of the node object, then the left attribute and the right attribute. So this represents the left and the right edges that I showed you in that diagram, that's binary tree diagram. So next off, we'll be looking at how we use this node class and how it works in the tree, and also every implementation done in this series is done in pseudocode. So this is the next stage of the implementation. So here we are creating a tree class. So this tree class is what is going to handle the tree instantiation or the tree objects or the tree data structure cloud. So inside it we have the initialization method, and it just initializes two attributes, which is the root. So like I told you, the root is where the tree grows from. So it's the root that gets every node that is going to be added into the data structure. So it's going to be stored in the root attribute. And the next attribute is the size attribute, which counts how much data is inside the data structure. So the implementation of a binary tree is too lengthy, and I don't want this video to be too lengthy because the size of information is going to be too large to digest at the same time. So I'll be cutting this video into bits by bits. So in the next episode, I believe that we'll be able to complete the implementation of a binary tree. So bear with me and also bear with yourself so that you can just have time to revise the past videos and revise the past data structures so that you can understand what is going to be going on in the further episodes. So thank you for watching the video, and don't forget to like and subscribe. Meanwhile, I'll be leaving some links to my repository on data structures. So in that repo I did an implementation of trees in Python and in JavaScript, but JavaScript more especially. I just did the Python implementation recently and I have not completed it, but the JavaScript is complete. So you can look at that and try to understand what we did in this current episode and in the past episodes, because you can revise other data structures, and inside that repo there are other resources you can learn from. There are algorithms, different kinds of algorithms, and different kinds of other abstract data structures that I may not talk on them in this series, but in the advanced course I'll be talking on them. I'm already producing the advanced course, so anticipate that. Okay, thank you for watching the previous video. I hope you learned something new. So in this series, the Acing the coding interview data structure series, note that this is an introductory course to the concept of data structures. An advanced course will be coming soon, so I'll be dropping the links in the description, and also check the links in the descriptions because they will link you to helpful resources that will help you find your grounds in this concept better. So thank you, and I'll see you soon on the next one.